Thank you, Vicky. Hello, everybody. Good morning, good afternoon, good evening. Here's Carsten, and I have some information for you about DNS encryption. So we will today talk about the need for DNS privacy, or what some people see as the need for that. And then about new acronyms in the DNS, something like DoH and DoT and DOQ, what that is. The most part will be about the current status of affairs, what software is available, and what is currently usable and what are the big players currently doing. And then I will zoom in into one recent development, and that was the Oblivious DoH and adaptive DNS resolver discovery that Apple is rolling out as part of their new operating systems, both on the mobile side, on the iPads and iPhones, and also on the Macintosh computers. So who am I? I'm a guy that is interested in DNS and DNSSEC and DANE and DHCP and IPv6. I'm a trainer and I support customers in doing so. And if being a trainer or being a consultant gives me still time, I go to RIPE and ITF meetings today virtually, in the past also in person, and try to keep up with all the developments there. And I then take that, distill the information, and I'll bring that to you. Now, one comment up front is that the whole topic of DNS encryption is quite controversial. And I won't go into that discussion, into that rabbit hole, may I say, because it is an endless discussion, and we can, do that. And I really, now I'm stuck. I don't really can solve that. So I'm trying to be neutral in this here and talk about the technology and where I see the technology might make sense. So privacy in DNS. So in the recent years, the IETF, the people who do the standards in the internet, they put more and more privacy features into the good old DNS protocol. And some of them we will discuss today, and we will see today, like DNS over TLS and DNS over HTTPS. Some others are also important, but that's not part of this discussion about DNS encryption, something like QNAME minimization or eDNS padding. So today it's all about transport encryption and what is being developed there. So why do we need maybe DNS encryption? Last year in summer, there was a study presented at the IETF Applied Networking Research Workshop. And in that study, the link of that study you will find in my long selection of links and resources at the end. The researchers found that about 8.5% of networks worldwide intercept DNS queries. And the number was higher in China and other countries, but total worldwide it was 8.5%. That is a significant number. They also found out that most queries are answered unaltered, meaning that the DNS queries were intercepted, possibly being looked at, but then the answer would be just forwarded to the client without any change. But once something like this is in place, some mechanism to intercept DNS queries, it's quite easy to also change the DNS answers later on. And that might be a problem in the light of censorship, in the light of privacy. So some people in the network, in the IETF, and also at DNS software vendors, they thought that this can be stopped by encrypting the DNS data. And that brought us all kind of new acronyms that you will see in the slides and also around in the discussion around encrypted DNS. So when we talk about DO53, that means DNS over port 53. That is the classic, almost 40-year-old DNS, which goes over UDP or TCP port 53. That's not encrypted. DoT is DNS over TLS, and that is the almost the same, or is the same classic DNS, but not sent over TCP and or UDP, but sent over TLS encrypted channels. And we will look a little bit deeper into DoT in a moment. And then we have DNS over HTTPS, and that is in so far different that it is also TLS encrypted, but it's at the same time also wrapped in the HTTP protocol, which is the hypertext transport protocol that we all use to fetch websites. And so we also look into that. Quite new and not really ready for prime time is DNS over QUIC, DOQ. QUIC being a new transport protocol originally invented at Google and nowadays being standardized at the IETF. And there are people who are working on making DNS over QUIC available once QUIC is available in operating systems. And then not really a new transport protocol, but also something to consider is DNS over cloud. That means DNS resolution via cloud services, something like Google Quad 8, Quad 9, Cloudflare's Quad 1, and similar services. So first, DNS over TLS. That is the DNS wire format, meaning the old good DNS that we have for 40 years, just sent over TLS over TCP. It runs on a dedicated port, port 853, and it gives us encryption and authentication, meaning it is encrypted. Nobody on the path between the client and a DNS resolver can look at the data and can see what is being queried. And also nobody can see what the answer is to the queries because the data is encrypted. We can also do authentication, and authentication is usually done from the client to the server, meaning the client authenticates that it's talking to the right server. In the way that DoT is implemented today, there is no client authentication, but that might be of interest in the future, so that a DNS resolver could identify the clients and might only permit name resolution for certain authenticated clients. The authentication can be done via the Internet PKI, that is the X509 certificates that we also use for the web, or it can be done via DANE, and that is then secured with DNS and DNSSEC. The alternative to DoT is DNS over HTTPS. And that is the DNS requests and DNS answers wrapped into HTTP, then sent over HTTPS port 443. And it's only standardized for the newer, the HTTP/2 protocol, not for the older HTTP1 or HTTP.1.1. So in order to make a DNS query, the client would send a HTTP request, something like https://server name /DNS-query, and then either sending the query data as a post or as a get with the parameters directly in the URL with question mark, and then the request directly in the URL encoded. And that gives us encryption and authentication, which is the same as for DoT, but it also gives us cloaking, meaning here that we can hide the DNS traffic in the other HTTPS traffic that goes over port 443, meaning all the requests for websites and the download for websites. And the idea here is that someone who doesn't like DNS encryption for whatever reason, is not able to disable it by blocking the port number. With DoT, which runs on its own dedicated port, it's very easy. Someone in the network could just block in a firewall port 853, and then DoT is not possible anymore. And because people want to use the internet, they will fall back to unencrypted plain old DNS on port 53. With port 443, it's not so easy because that same port is being used to download websites. And if someone is blocking port 443, for the average user, the internet is kaput or internet doesn't work anymore. So the idea here is to make it more censorship resistant by using the same port as websites, web requests. Also, the people who worked on DoH on the protocol made it look like normal HTTP traffic. So usually DNS requests, for example, are smaller and lighter than the HTTP requests. And also the answers are smaller and lighter than an average web page today. But in DoH, the DNS data can be expanded, can be padded with extra data that doesn't need to be there, but just makes the answers and the request bigger so that it looks like more requests for websites. Another important point for the success of DoH is that it is possibly easier to implement for client developers. Because client developers, they already know HTTP and HTTPS, and they have already libraries in their programming languages that can talk to web servers. And they talk HTTPS, and DoH does the same stuff. So if you already know how to develop that in your app, you can easily do DNS requests. And that gives you, as an application developer, more availability or more options to use the DNS than going through the operating system, because the operating system has a rather fixed and not so rich API for doing DNS. And with DoH, you can utilize the whole DNS. You can, for example, directly ask for SRV records or TXT records, something that is not so easy while going through the operating system. And also DoH enables developers to do name resolution directly on the application level, that is bypassing the operating system, which some people think that is bad because it creates different name resolution options, and it's very hard to troubleshoot from the network point of view. And that could lead to a network which is much harder to maintain. We have to see how that works out. So because DoH has good sides and bad sides, people are wanting to control the use of DoH in their networks, and that is possible. One option to do that is to use a so-called canary domain. And the canary domain means that if a certain name, the name of the canary domain, cannot be resolved, then the network doesn't want DoH or other encrypted DNS in their network. For the Firefox browser, that domain name is use-application-dns.net. So a Firefox browser that can talk DoH and might do so automatically without asking the user first, it will try, when it starts up, it will try to resolve this domain name using just classic DNS. And if it can resolve that domain name, then it thinks that this is an unmanaged DNS network, and DoH, DNS over HTTPS, can be auto-enabled. But if the domain name cannot be resolved, then someone actively has blocked that domain because it's available in the internet. So this is a managed DNS network, and DoH will not be enabled. However, users can still go into the preferences of the browser and enable that. Now, this is the way how Mozilla with the Firefox browser choose to implement the canary domain. And the IETF is currently discussing similar signaling functions in order to inform applications about the filtering policies for DNS and for DNS resolvers. Besides looking for the canary domains, Firefox also does other checks before enabling DoH. For example, it looks for the safe search variants of the google.com and youtube.com websites and sees if the network redirects to them, because that would also be an indication that this is kind of a managed network and people want to have certain special DNS resolvers that have security functions in there. On the Windows and macOS operating systems, Firefox tries to detect popular parental control software that is running on the machine. And if the Firefox browser is in an enterprise network where an enterprise policy has been rolled out for the browser, then it is also not, it will not enable DoH. So that was about the Firefox. How does it look on the other operating systems and browsers? For Firefox, it is using Cloudflare as the default option for a DoH. There's also an option to use NextDNS. And there will be Comcast Xfinity as a third partner that customers and users of Firefox can choose as their DoH server. And the automatic rollout started in February 2020 in the US. It will, at some later point, or maybe it has already started being also rolled out in the rest of the world. But I have currently no information if that already has started. Still, if you want to use DoH in Firefox, you can go into the preferences there and select the DNS over HTTPS, select either one of the pre-configured partners or put in an IP address or domain name of some other DoH server that will then be used. All the Chrome, the Google Chrome browsers and browsers that build upon Google Chrome, they implement DoH, which are Opera, Vivaldi, Brave, Microsoft Edge, and Bromide. And these browsers will try to auto-upgrade the configured DNS resolvers, the ones that the operating system has learned through DHCP or manual configured or router advertisements in IPv6. They will check whether they also support DoH, and if they do, if they have port 443 open, they will use that, and if not, they fall back to classic unencrypted DNS, DO53. Google is currently experimenting also with the adaptive DoH resolver discovery, similar to what I will explain later on in what Apple is using today. The latest insider builds of Windows 10 have support for DoH, and Microsoft plans to make that available to the general public in spring next year, spring 2021. Currently, you can only put in IP addresses of certain DoH servers that are coming with the operating system. However, on the command line, it's possible to add your own, or add your own DoH servers to a permit list, and then you can go into the GUI and also select other servers other than the ones that Microsoft delivers with Windows 10. And this is how the GUI looks like. So it's possible here to configure the primary resolver and the alternative resolver. And you can put in IP addresses there and then select whether you want to have classic DO53, or if you want to have encrypted DNS with fallback to unencrypted DNS, or if you want to have encrypted only, which is the one that I've used here when I made this screenshot. And you have that for IPv4 and the same settings for IPv6 as well. On Linux, Linux was one of the first systems that implemented DoT, DNS over TLS, and that's in systemd resolved, which is part of all the modern Linux distributions that have systemd. So it's in Red Hat 8 and Ubuntu and SUSE and Arch Linux and Debian. They all have systemd resolved. However, it is not enabled by default. The user or the administrator needs to go into the system and enable systemd resolved that it is actually being used. Another downside here is that it's opportunistic mode only, meaning it does always an automatic fallback to unencrypted DNS if the encrypted DNS fails. And that opens the possibility of a downgrade attack. As well, there's no server authentication. So the client, the systemd resolved, doesn't authenticate the name of the server against the certificate the server is presenting. So there is a possibility of man-in-the-middle attacks. The whole DoT support can either be configured global or per interface. So you could configure DoT on the wireless, but not on the Ethernet. And yeah, it's not enabled by default. On OpenBSD, there is DoT support in Unwind, which is also an operating system resolver that comes with the system. And it's also not enabled by default, but it works better than the Linux part because it has either opportunistic auto update, or you can configure it into strict mode. And in strict mode, it will only do encrypted DNS and nothing else. It will not fall back to unencrypted DNS anymore. And it does authentication of the certificates of the server via the TLS certificate. So no man-in-the-middle attacks and no downgrades. On Android, DoT is available in Android 9. And it's a manual setting, so the user needs to go into the preferences of the Android system and enable secure DNS there, or a company can roll that out as a company policy. And once that is configured, it will auto upgrade to the configured DNS servers, or it will use the Google DNS servers as a fallback. And rather lately this month, Google has started to implement DoH as well. That in the Chrome browser that comes with Android. And that is enabled and available in Chrome on Android version 58 and up. And that has been released in September or this month. And that also does auto upgrades on the configured DNS resolver. And then the Apple macOS and iOS versions, the new versions that are coming out this September, they support both DoT and DoH. And it's possible to select the use of encrypted DNS either globally or per app or application. Global configuration has a higher priority as a per app configuration here. So only if the global configuration is left alone and untouched, then an application can override this and use DoT or DoH themselves. If the global configuration either strictly requires encrypted DNS or does not permit encrypted DNS, the applications need to take care of that and that policy. So it's possible to deliver encrypted DNS configuration via apps. So ISPs and telco providers can offer certain apps that will automatically configure the mobile devices to use their DoH servers. And what's quite new and which we will look deeper into in this webinar is that the operating system can also learn per domain DoH and DoT settings via DNS or HTTPS, and that is the adaptive DNS over HTTPS, which I personally find quite interesting. Other ways to discover the servers is via DHCP or provisioning domains, or queries to the resolver.rpar name using classic DNS53. All these discovery methods are currently still in active discussions, so nothing that Apple has implemented here is set in stone and is actually an internet standard. Apple is actively working in the IETF working group there. As far as I understand, they will adapt whatever the working group is deciding as a final standard then. That was the client side. On the server side, we have, of course, Bind. And DoH and DoT support is currently in the development branch. So the 9.17 branch of Bind is the development branch, not for production use, but DoH and DoT is currently being implemented there. It's not ready for testing yet, but it will be later this year or beginning of next year. And then the upcoming version 9.18, which is scheduled for early next year, will then contain the production DoH and DoT support. And also, IC will backport the support to the extended support version, which is the version 9.16. Unbound, another quite popular open source resolver, does support DoT since ages. I wrote here since 2017, but that was just that the name changed to DoT at that point of time. Unbound had support for DNS over SSL via port 443 a long time before that. So that has been a long time there and is quite mature. And support for DNS over HTTPS, DoH, has been just merged last week. So it's new in there, and it will be out to use in Unbound version 1.11.1, which is scheduled for October this year. What about the other DNS resolvers that are out there? Now, it is possible to upgrade any existing DNS resolver to DoT or DoH by putting a DoH or DoT termination endpoint in front of that existing server. So some software or some hardware that terminates the encryption, very much like a reverse proxy is doing for large web servers. And then in the background, it will just talk plain old DNS to the existing DNS resolver. And one open source software that can be used to do this is a DNS dist from the Power DNS people. That is an open source DNS load balancer that supports both DoT and DoH. I've also seen some of the commercial TLS load balancers that are used for both DNS load balancing, but also for web load balancing. For example, the products from A10, but also others, they support DoH and DoT. And because they have special ASICs and do it in hardware, they can terminate TLS traffic in huge numbers. And Nginx, which is a popular open source web server, and it's also a protocol proxy, does support both DoT and DoH and can be used to as a DoH or DoT front end to any DNS resolver. And I collect a list of DoT, DoH implementations, and you can find that list on the link here on the Encrypted DNS implementations page. And I think there's roughly 30 different implementations of DoH and DoT available in different flavors, operating systems, and functions. So now we have a deeper look into adaptive DNS over HTTPS, which is the implementation that Apple is rolling out. So the goals of adaptive DNS is that no party other than the client or server, server being the resolver, can learn or control the names being queried or answered. So nobody in the middle of the communication should be able to read what's being requested, and nobody should learn what's being answered in the DNS between a client and a resolver. And only a designated DNS resolver associated with the deployment that is also hosting the content will be able to read both the client IP address and the queried names. Now, the idea here is if we, as a client, request a DNS name, let's say for a website, then we do that because we want to make a connection to that website. So the web server of that website, let's say that is for the company example.com, that web server will learn our IP address anyway, because we will make a direct connection with our browser to that website. So we don't leak more information when we send a DNS query to a DNS resolver that is also operated by the same party than the example.com company that is also operating the website. And that is here meant by having a designated DNS resolver. So the protocol tries to route the DNS queries in a way that they will end up, even on a resolver side, if they are not locally resolved, but somewhere in the internet, in the larger cloud resolved, to route the requests to a resolver that is operated by the same entity as the web servers. Also, it is important that the clients will be able to comply with other policies, something like VPNs or local networks that have that are authoritative for private domains. So the classic split DNS mechanism where local networks have their own DNS namespace, which is not exposed to the larger internet, and that should still work. So it's not a solution that sends everything out in the internet to some big resolver, and that then is not able to resolve the names of the local Active Directory. So how does a client learn about the designated DoH service for a domain? Now there are several options here. For example, it can be learned through DNS itself. There are two new resource records, the HTTPS resource record and the SVCB resource record. Both are very similar. The difference is that HTTPS, it's like the name says, it's more tailored for web request, and SVCB is the more general case that also works with other protocols other than HTTPS, so mail, chat protocols, etc. A client can also learn about the designated DoH server for a domain through a HTTPS header, the alt SVC header coming down from a web server with a website. There could be a well-known URL to use a DoH server, and also it can be part of a local provisioning domain. Besides giving information about the designated DoH server, the HTTPS record also does a lot more, and it has not been developed for DoH. It's just a side effect that it can also be used for the DoH case. The original idea of the HTTPS record is to eliminate additional round trips to the DNS. Because nowadays, in order to make a connection to a website, a browser needs to send 2 DNS queries, at least, one for IPv6 and one for IPv4. And it does so with happy eyeballs, sending the IPv6 DNS query first, so the query for the Quad A record, and then a short time after that, it sends the same query, but for an IPv4A record, again to the DNS. In the future with HTTP3, with QUIC, because QUIC is implemented over UDP, not TCP, it's not possible to do to convert a TCP HTTP2 request directly into an HTTP3 answer. There is the requirement for a browser to learn before the first request whether the server supports HTTP3 or whether the server supports only the older HTTP2 or HTTP1 protocols. And that can also be in the new HTTPS record. Then the HTTP record also transports public keys for the web server, which are used to encrypt the client hello, which is the first part of the TLS handshake that is currently going unencrypted and is still a little security issue or privacy issue, let's say. And also other data can be returned with the HTTPS record, such as the encrypted DNS resolver hint. So here we have an example of how an HTTPS record will look like. Also nice is that HTTPS records can be used to create an alias on the start of a domain, something that is not possible with CNAMEs, but something that a lot of people always wanted to do. So for example, if you have a website, company.com, and you also own company.ca for Canada and company.org and company.de for Germany, and you don't want to operate or you don't want to maintain all these DNS zones. Instead, you want to have just the company.com and just alias all the other names to company.com. That is not possible in classic DNS with a CNAME, because you can't have a CNAME on the top level of a zone name. But you can have that effect with the HTTPS record. You can use that to alias one domain name to another domain name, and that can be on the top of the domain. Only for web traffic with HTTPS, but that is what most people want anyways. And then here we have an alias from example.com to svcexample.net, and then on svcexample.net we have the HTTPS record. I won't go into details here what the different fields are, but we see here the DoUri, which is the URL of the designated DoH server for that domain example.com, and we have also the ODO key, which is an encryption key being used to make contact to the DoH server and to encrypt the query. So that was what Apple is implementing, is Oblivious DoH. That is an extension to the DoH that we already discussed in this webinar, and that allows client addresses to be disassociated with the queries. And here's the link to the internet draft, and I have made a little graphical representation what's going on. Now this picture looks very complicated first, but at the end, in the end, the whole protocol is not much fatter than the classic DNS, because at the end we just have two machines that work together in order to resolve a DNS name, one resolver and one authoritative server. It's just that the different functions, I've put them here into different server icons for clarity. And also at the boot time of a client, something happened to discover the designated servers. So it all starts with the client booting, and it is then asking for the HTTPS record towards the classic DNS resolver that it has learned via DHCP. Now in this graphic, it still talks about the HTTPS SVC record. That record has just recently been renamed to be the HTTPS record. So every time you see here HTTP SVC, think it's the new HTTPS record. So we ask for that record for resolver.arpa, and that request gives us the information about the local DoH servers in the network. That would be the DoH server just right beside the classic DNS server there. Then it's also possible to learn about more DoH servers in the network with the provisioning domains through IPv6 router advertisements. Now the client has learned about a local DoH server. It will probe that DoH server and will see if that is really available. Next, the client would like to contact some resource at vendor.com, which is maybe the vendor of the operating system of the client machine. So it asks for the HTTPS record through classic DNS and validate that through DNSSEC, and ask what machine is the designated DoH server for the name vendor.com. That request goes to the classic DNS resolver and then will be resolved through the authoritative server for vendor.com. And the answer is coming back with a list of vendor-approved DoH resolvers and proxies that can be used. In our case, it is DoH example.xyz and DoH example.com. And that list is being given back to the client. And now it's important here that we have this proxy and the end resolver that is designated. The important one is the designated DoH resolver, not so much the proxy. The client needs to learn about some proxies and might be pre-configured with some DoH proxies. But the important one is the DoH resolver. Now, the client wants to query some name in vendor.com. So it is asked for the IP address. It needs to have the IP address for the resolver. So it asks also for the HTTPS record for DoH example.com. And it gets a response with the IPv4 address, with the IPv6 address of that server, and also with a list of domain names this DNS resolver is designated for. And it checks whether vendor.com is a part of that. It also receives the public encryption key for that server. And that is important because we will use that public encryption key in a moment. And that answer coming back is DNSSEC signed and will be DNSSEC validated on the client. Now the client is sending, and this is now the real DNS request to find the resource at the vendor. It asks for www.example.com and it sends that request to a proxy, to the DoH example XYZ proxy. And it will encrypt the query with the public key it received from dohexample.com in the previous conversation. So the proxy, the DoH example XYZ, it sees the IP address of the client, but it doesn't see what's being asked for because the request is actually encrypted. What it will see, something like, please forward this encrypted request to the server dohexample.com. which it then does. It takes the request from the client and forwards that to the DoH-example.com server. That server, because it's in possession of the private key that matches the public key, that server then can decrypt the request and finds, oh, this is actually a request for example.com, and it sends that request to a classic authoritative DNS server for example.com. The authoritative server sends back a classic unencrypted DNS response to the DoH resolver, and that DoH resolver will now encrypt the answer with the client's public key. That was the client's public key was also in the original request. And then the DoH server, the designated DoH server, will forward that request to the DoH proxy server. And the proxy server is the one that knows the IP address of the client, but it will not be able to look in the answer because, again, the answer is now encrypted, and it's encrypted with the client's public key. And it can only be made visible with the private key, which hopefully only belongs to the client. So the proxy sends the request back to the client, and the client can decrypt the answer and will see, oh, that's the IP address of example.com. So we can make an HTTP request to that web server. This is very similar to the onion routing network, to Tor routing, because we have kind of onion routing here. We have different layers in the DNS request, an outer layer where the client is sending the requests to the proxy, but the proxy will not see the inner layer, which is the actual request. It can only look at the outer layer, which tells it where to forward the inner layer to. And then it will be forwarded, and then the outer layer will be stripped off. The inner layer will be visible to DoH-example.com, to the actual DoH resolver. That will be able to decrypt and then answer the query. And on the way back, it's being wrapped again into this kind of onion layer package. And it will be sent back to the client, and the client, being in possession of its private key, can decrypt all the conversation from the resolver and can make the data visible. With this scheme, with this protocol, neither of the servers on the right side knows both the request and the answer and the IP address of the client. Every server just knows one bit of it. Some servers know the query, but not the IP address. And some servers know the IP address, but not the query. And that's the whole idea behind the Oblivious DoH. And here our web server is answering with website, and that website or the headers coming back with the website can have additional information about the DoH infrastructure. So, and this concludes my little webinar on the update of encrypted DNS. I hope you liked it. Here I have this link to resources, and you will find there all the IETF documents, interesting blog posts by various people, and videos of discussions around adaptive DNS and Apple's implementation of Oblivious DoH and more.
So Carsten, seeing what a fabulous list of resources and references you have, I think I can easily send out a follow-up email to this webinar to everyone who attended. I think I'll include a link to that list of references because that looks like a great list. And I don't want people to have to go find the PDF of the slides and cut and paste it. So I want to thank you. That was really an excellent, quick introduction to a incredibly complicated topic. And I also appreciate the fact that you didn't waste time, as you said, you know, digging in the politics of the situation, because this whole discussion has been incredibly political, and sometimes it's hard to just focus on what the technical proposals are. That said, we do have some questions in the chat. I don't see any questions in the Q&A yet, but let me just take a look at the chat. I think everything that was asked in the chat you subsequently addressed, but let me just take a quick look. There was a question, I think there may be a typo in this from Simon. How do you avoid a hijacker to hijack one of the trusted resolvers, the TRRs? You know, that's sort of a meta question about, but anyway, do you want to?
Yeah, the idea here is because it's TLS and it's HTTPS, the servers have X509 certificates. And it's the same question about hijacking web servers. So the idea here is that we have the certificates on the servers, and the clients can verify the certificates. Now, it is possible, same as with web servers, that because of the security breach, an intruder breaks in and takes over the server. And that's bad. And that needs to be counted with, yeah, security on the machine, because if a trusted resolver is taken over, then there's nothing the client can do about that. And as long as the intruder just leaves the certificate in place, also that's not detectable. One thing the client should still do is do DNSSEC validation, because then the trusted resolver could not change the DNS answers without being detected, at least if the DNS zone where the answer is coming from is DNSSEC signed. Both encrypted DNS and DNSSEC are complementary protocols. So it's not that encrypted DNS is replacing DNSSEC or the other way around. Both work together. Yeah, but that's a tricky one, because whoever operates a DoH server must make sure that that one is not taken over by a malicious party.
Presumably that's part of the process that they use in deciding what are trusted resolvers, is looking to see what they think are fairly well defended. Another excellent question, how can the security settings be implemented on the new transports, such as RPZ or DNS rebind protection?
Yeah, this is why I recommend everyone who operates RPZ or rebind protection to also enable DoT and DoH on their DNS resolvers, because how most clients currently work is that they first probe the local DNS resolver that they have learned via DHCP or other means, and they check whether these servers do DoH or DoT, and if they do, they will be used. Same is with the with Apple's operating systems. I haven't gone deep into all discoveries, but it is possible to tell Apple operating systems that there is a local DoH resolver in place and that should be used. And then encryption happens between the client and the resolver, but on the resolver, it's not encrypted anymore. So if you operate the resolver, you can have RPZ, you can have rebind protection and all other stuff that you want to implement security-wise on the DNS resolver. Only if you not implement DoH or DoT, then the clients might go into the cloud, might go to some other services, which is not your service, and then you are out of the loop.
Okay. Another comment, really. Another from Rui. Another problem of DoH could be in a bring your own device environment.
Mm-hmm.
He says, we used to have a lot of tickets from people that forced use of Google servers in order to evade the ISP's DNS filtering.
Mm-hmm.
So it's a problem of DoH, or I guess in this case, from the client perspective, an advantage.
Yeah, this also depends on whether then the clients, the bring your own device clients, whether they will get the information from the local network that there is a DoH or DoT server locally that they can use. And if that's not the case, they might go outside and use Google or use Cloudflare or some other cloud DNS resolver.
Yeah. The last question I see is one from Simon about what is the new HTTPS resource record, and right after he asked that question, you addressed it.
Okay.
So I think that's it for the questions. I didn't warn you about this, but I posted a little poll just asking people what their deployment plans are. I'm just going to end it right now, and then I think people will be able to see the results. There we go. So I was just asking what people's deployment plans are. 13% only, we only had 24 people vote. Three of the folks that are on the line have already deployed DoH. Additional 4 are planning to deploy it real soon now, within the next 6 months. Then there are 5 more that are planning to deploy it, maybe more than 6 months out. So presumably a little more testing time. And then about the same number of people on the call at the moment don't have any plans to deploy DoH. So, about half and half either in the have decided to deploy versus haven't decided to deploy. I think, one of the key things about DoH, and one of the reasons it's so controversial, is your users might use it even if you don't plan to deploy it, unless you implement the canary domain. So that's why everybody needs to know about it, whether or not it's specifically something that you're planning to pursue. So do you have any other comments, Carsten, or if not?
Yeah, this is when now I'm following the discussion around encrypted DNS for multiple years. And I thought last year that now it's done and it will be rolled out, and it's not perfect. And yeah, people complain about it's not being perfect. But I've seen this year, there was a lot of new discussions and also new implementations and new ideas, good ideas coming there. So it's not really finished, and it's not really discussed to the end. Still, it is being rolled out, and I would even already say it's pushed out by big vendors. So we can't ignore it, but we should keep eyes and ears open what the future will bring. And yeah, maybe we will have another update next year at this place.
Yeah, I know one
Yes.
concern among people who are looking to deploy this is about the scalability. So one of the beautiful things about plain old DNS is that it, because it relies on UDP, it's pretty scalable. So anyway, I know that is one thing that people are looking for, is information about the scalability of these new services.
Yeah, we will need more CPU power and memory, a lot more memory for at least at the beginning. There will not be so much DoH and DoT traffic. It will grow slowly, maybe faster now that Apple is bringing that out. But at the end, if all the DNS or even half of the DNS traffic we see today is going over DOH or DOT, that will require much larger DNS resolvers.
One other thing I just wanted to mention, even if you're not planning to deploy this within your network, if you are an enterprise DNS team and you have a lot of employees that travel, that are working outside of your network using untrusted Wi-Fi, places where you're concerned about their DNS traffic revealing things about what they're working on, this might be a good option in that kind of case.
Yes, this is the good part, because here you can get all your roaming users that are roaming in foreign networks to use your own DNS resolve with all the security, with all the RPZ and rebind protection and other security mechanisms in there, which is not possible with classic DNS. So yeah.
Okay, well, thank you. Thank you very much, Carsten. This has been a very informative webinar. And just to reiterate, I will send out an email probably Friday, a follow-up email with a link to the recording and Carsten's list of resources that were at the end of his slide. And we will also post a PDF of the slides themselves on our website.
Thank you, Vicky. Thank you, everyone, for listening. Have a good day.